Welcome to our NPTEL lectures on the power quality improvement technique. This is going to be our second lecture on the multi-level inverter. We have discussed about the diode clamp multi-level inverter. We are going to discuss now the capacitor clamp multi-level inverter. So, this is the capacitor clamp as you have seen that, but there is a change in the topologies, but component count is less. You had two diode connected from this anti-parallel fashion. Mostly you have a diode here and you have a diode here, and this is the time of diode and you have a connected here. So, you have a two diode, instead of that you have only one capacitor, and thus component count is the one of the biggest advantage here. So, you have a least component count, number of diode goes abysmally high in case of the diode clamp multi-level inverter. If you go for the more than 5 or 6 level. So, for this reason, we look for the different multi-level solution, and that is the capacitor clamp, and here there is a little change in the logic. Generally we have seen that this S1 and this one are complementary and this S2 and this one is complementary. Here you will find this switch and this switch is complementary, and this switch and this is complementary. So, let us see how does it work. Here upper one is same, there is no difference here. You apply S1 and S2 should be closed and you get the value of the VDC. And so, this is the same as the diode clamp inverter, but there is a change in the switching while you want to get a 0 voltage or the neutral voltage at the pole of the inverter. Then you will connect S1 and S3, as you have seen that these two switches will be complementary, and thus there is no cause of this should be acting. Thus what happen, ultimately this capacitor, all the voltage it will take by capacitor. So, this voltage become VDC, and thus what essentially you get is a 0 voltage. Similarly, so you get a 0 voltage here, and you can generate that 0 voltage, also there is a redundancy through S4 and S2. Same thing here. So, this switch will be on and thereafter this voltage will come and this. So, there is a redundancy, thus you can generate this voltage by combination of S1 S3 or S4 S2, where generally S4 is nothing but S1 prime you can also write, and you can write also it is S2. And this one is same, there is no difference between these two. So, you require to switch it on, then you have to switch it on S3 and S4 and you get minus VDC. So, one of the advantages is that component count is less, you generally made it with the two diodes, here you have a no diodes, only one capacitor, and you want to have a controlled voltage across it, that is one of the challenge, otherwise it works fine. And you also have a redundancy. So, you can generate, you can reduce the switching losses by the 1 bit change, and thus you can generate this 0 voltage by combination of S1 and S1 and S2 prime or S3 or S2 or S1 prime or S2 S4. So, this is all it is possible to derive in case of this flying capacitor. So, what does it say about us? The voltage level redundancy can be used for the extra degrees of the freedom, that is what we have discussed here. To control and optimization purpose, because you can reduce the switching losses with these redundancies, and also the redundancy gives you more reliability. If some switches is not working, you can bypass and still you can function very well. Flying capacitor multi-level inverter also offers output voltage waveform lower THD and DVDT. It is same as your direct clamp inverter. One of the major disadvantages is that require large number of the bulky DC capacitor with a separate pre-charging unit. So, that is something you require to have a VDC that comes into the pictures. So, and you require to always maintain that voltage. So, that is something, and after some interval of time capacitor always have a weakest link into the component count. Generally longevity of this capacitor is least compared to the other devices, and for this reason we sometimes find it is difficult in terms of its main breakdown time and also reliability. The DC capacitor voltage in the inverter vary with the inverter working conditions. Sometimes current goes out and sometimes current sink into it, that what you assume that capacitor voltage is also constant, that is also not so, and thus you require to have a balancing networks. So, for this reason we say that complex capacitor voltage balancing is required to control this flying capacitor MLI. Now, let us go to the cascade H bridge MLI. So, one of this advantage of it that you got a blocks, you just put them block, it becomes a functional purpose. So, for the 5 level, for you can have this E and E that constitute the phase A. Similarly, this will constitute phase B and this constitute phase C. If you see that number of switches in the 5 level is you require. So, this is a 8 switches per phase. So, you require the 24 switches. Otherwise, you do not require, generally this anti-parallel diode comes with the switches. So, you need not have to connect any extra anti-parallel diode, and also the capacitor. I shall list out the component count after discussions of all these inverter topologies. So, let us see that this E, all those voltages are equal, we assume to be so, but it may not be equal, you can change it. And another problem is that we require to provide isolated voltage source for each of these blocks or the H bridge. So, we can say that it is formed by the series connections of 2 or more single phase H bridge inverter, a single H bridge or converter, whatever may be. The single H bridge converter is able to generate 3 differential level of voltages. Once you switch it on, this voltage and this voltage, you generate a voltage. If you switch it on this or this, you get a voltage. If you switch it on these 2 voltages, at this point you get a 0 voltage. So, thus you get a 3 level of voltage, same for it. So, the combination makes you the 5 levels. Each leg has only 2 possible switching states to avoid DC-link short circuit. Total 4 different switching states are possible in a H bridge, just I show in the next slide. See that this is for one H bridge 1, let us say. You can switch it on this, and thus what happen, you get a VAN. You can switch it on this too, ultimately you can get the 0 voltage, and then you can switch it on this, you get a negative voltage, where K are the connected level of the bridges, and you will generate K plus 1. So, you have a 2 such H bridge in per phase. So, 2 K plus 1, that is essentially 5 level. Different voltages are obtained and the maximum output voltage will be K into VDC. So, you got VDC plus 2 VDC, where VDC is the input voltage of the single bridge and voltage stretched across the individual device will be VDC by 2. That is also a very big advantage in terms of the BOM cost. So, what is the advantage of it? Advantage is its modular structures. So, you just put them like a bricks and build the house. Enable the fault tolerant operation, we can show that redundancy is more, because different voltage level can be generated with the combinations, few more combinations. All the semiconductor only block the voltage level of VDC. So, effective increase in the output voltage and power level can be enhanced, and also it enables us to, if you put the more bricks and you can increase the voltage rating. High voltage operation without switching device in series, but drawbacks are each H bridge inverter needs an isolated DC source, high component count, CHP inverter uses large number of IGBT modules. These are the few disadvantages of this proposed H bridge MLI. So, how does it generates? Let us see. That is a 9 level. So, if you want that this switch and this switch should be on, let us say that it is generating VA1, and once you want, you just spread it over little bit and you generate VA2 same way. Similarly, you get a VA3 and VA4, you add them. So, you get a staircase kind of waveform, and same way for the negative half cycle, and thus you also get a stairway kind of waveform, and it is quite close to the sine wave. For 9 level we require 4, because it is 2 k plus 1. For 9 level symmetric H bridge MLI, that is multi level inverter, 4 bridges are required, and ultimately VA1, VA2, VA3, VA4, these are the all switches. More the number of the redundant voltage levels are possible, and the structures is modular. If you want that instead of the 11 level you just connect another bridge, you get 11 level. Now, there is another way to do it. This is called the cascade H bridge MLI with the unequal voltage, and that also help you to shape out some kind of level of some kind of steps. So, see the beauty of it. So, this can be upper one, someone you get a steps where it is not on. Thereafter, once you on it, you get some voltage. This voltage is 1/3 of this voltage, and it is quite easy to do because and it is it has a huge applications in solar inverter topologies. And nowadays, as I told you that solar inverter, now we will integrate the power quality problem with the renewable energy in the microgrid. Since shunt active power filter, it can be a shunt active power filter, and once you, instead of the capacitor, you can have if you connect you can keep this capacitor voltage to that level by actively controlling it in case of the shunt active power filter, and you can do it by also putting the solar panel. You can put the one panel or you can put the 3 panel, and thus you can say that you have a great merit on it. So, you see that how you generate a different level by just with the 8 switches. That is the beauty of this unequal DC voltage, but it has to be separate. So, you give a negative, you get a positive, you give a negative, you get a positive, and thus you generate this square wave. So, what should be the level of the voltage, and thus you get a multi-level, multi-steps inverter. That optimization is also a great scope of the research, and you find plenty of research paper on it. So, for the 9 level CHB MLI, only 2 H bridge are required. That is the beauty of it. So, DC voltage source should be different magnitude, that is a challenge, but solar it is not a challenge. Modulity structures is lost, that is one of the disadvantage. If you want to have another voltage, so you have to put in a DC bus level, and generally this device rating also will be different, because you do not have a, you do not want the same kind of switch. The voltage trace across is a 3 VDC, here is only VDC. Loss in redundant voltage level, and switching pattern is quite complicated, but with the help of this now modern control circuit like FPGA based systems, where implementing algorithm is quite easy. So, that is easily possible. So, that is the one of the area of the research. So, with a less number of cascade H bridge, you can generate multi-level, you can generate different level of the inverter. So, now let us invest our time on the PWM technique that is suitable for your multi-level inverter. So, multi-level inverter modulation can be broadly classified if it is, if you are using, that is selective harmonic elimination we have discussed already. So, if you are using GTO for the higher rating, then this we prefer low switching schemes, and for the higher switching frequency, this is IGBT is been used, you can go this method. So, this is selective harmonic eliminations, generally it is sub 1 kilohertz frequency, and here the frequency range is 5 to 10 kilohertz. So, you got a SHE, thereafter nearest vector, thereafter nearest level shifting. These are the few technique. With the sake of time, we may not be able to discuss all those methods, and we can combine, that is high frequency, that is called hybrid modulations. Thereafter we can have a multi-carrier PWM. We have discussed the phase vector, this space vector modulation. We just touched upon for the 3 level inverter. Students are requested to go through those lectures again. Then phase shifted PWM carrier, level shifted PWM carrier, and mixing this, you got a hybrid PWM carrier. Now, first let us take a phase shifted PWM carrier. If you have a multi-level inverter with m voltage level, it requires m minus 1 carrier. For 3 level you require 3 carrier, for 5 level you got to have a 4 carrier. All the triangle carriers have frequency and same peak amplitude, and generally they have been phase shifted. In phase shifted PWM carrier, the phase shift is by the phi CR, where phi CR is 360 by m minus 1. So, for the 5 level you can have a 90 degree, because m equal to 5. So, m minus 1, it gives you a 90 degree phase shift for 5 level. Modulating signal is usually a 3 phase sinusoidal wave with adjustable amplitude and the frequency. We can see that later in the next slide. The gate signal is generated by comparing modulating wave with the carrier wave. So, this is the waveform where this dotted line are the carrier. This one is a first carrier wave. Thereafter you will have another carrier wave, but by some phase shift, and this is the 90 degree phase shift. So, you will generate 4 carrier wave, and this is the carrier wave 1, this is carrier wave 2, this is carrier wave 3, and this is the carrier modulating wave. So, now they are 120 degree phase shifted here, since we have a 3 carrier wave. So, you will generate this pulses. Once logic is pretty simple, the PWM, when this modulating signal is more than the carrier wave, you will be on. Thus, you get Vg1 for this purpose, and it will be on till this time, and here crossovers occurs, and ultimately this will be the pulses for the first H-bridge converter. Similarly, this is the carrier wave for the Vg1 and the Vg2, and that is coming from this place, and this is the Vg3. So, ultimately you will generate this voltage as in the second cascade H bridge. Similarly, for the third carrier wave, you just compare and you will generate the third carrier wave signals. I request you to simulate these circuits, these logics, then only you can generate the gating signals very easily, and thus you will get these voltages. Ultimately, VAN will be 3V, it is VH1, VH2, VH3. So, this is the voltage level you will get. So, As we know, we have studied your PWM technique from the power electronics courses. So, there is nothing new here. Amplitude of the modulation ratio is defined by MA, that is Vm by Cr, where Vm and Cr are respectively the peak amplitude of the modulating and the carrier wave, and the frequency modulation ratio is defined by Mf Fcr by Fm, where Fm and Fcr are respectively the frequency of the modulating and the carrier wave. The device switching frequency can be calculated SWDAV equal to the carrier wave frequency, modulating frequency into MF. Generally, it has to be the multiple of it, otherwise intraharmonic will come. So, for this reason we require to avoid that. So, for this is the spectrum for the level shifted PWM, phase shifted PWM, sorry, thereafter we will take out the level shifted PWM. So, this is for the 7 level cascade H base converter or inverter. The harmonics in VH1 appears the sideband containing 2 MF and multiple of 4 MF, 6 MF and so on. This is the case, and you can see that voltage harmonic is as high as 53%. Thereafter, if you feed it to the machines, the machine longevity will be 1/3. The harmonics in VAN and VB, that is the phase voltage and this is the line voltage, appear at the sideband in and around that in 6 mm. So, this is the case here. And triplet harmonic such as 6 mm plus 3 and does not appear in AB. Thus, it has a scope to inject third harmonic injection to better utilizations of the DC bus voltage for the drives applications. So, this is the some observation we can do in case of the phase shifted PWM. Now, the frequency of the dominant harmonic in the inverter output voltage represents the inverter switching frequency, that is the 5 kilowatts or 10 kilowatts, whatever it may be, and for the 7 level CHB you will shift it 6 times. So, it will be 6 MF into MF, that will be 6F. So, that is the advantage of it. So, effectively you are switching 2 kilowatts and effectively your sideband lies at 12 kilowatts and you require to design the filter at 12 kilowatts, and thus size of the filter get reduced. So, we can conclude one of the basic advantage of it, that high value of switching frequency allows more harmonics in AB to be eliminated, while low value of switching frequency helps you to reduce the device switching losses. So, once you are switching at less frequency, your switching losses are less, and but your voltage has higher spectrum, 6 times more. So, what essentially we require to use a lower filter size, and this is one of the greatest merit of this cascade H based multi-level inverter fitted with the phase shifted PWM. So, it is just like made for each other. So, in general for a M level inverter, so switching frequency, this is the something that we require to use it frequently. Switching frequency inverter equal to M minus 1 into switching frequency of the devices. So, the switching frequency of devices is quite low. If you have a 9 level, then it is 8 times. And The maximum fundamental frequency voltage RMS can be found from VA1 max equal to 1.224 into VD, that is 0.162 m into E, and the maximum value of, you know, that carrier wave magnitude equal to the modulating wave magnitude. So, that will be equal to 1, and then in that case you can get this magnitude of the voltage, and that is quite high. So, thus we require to conclude the advantage of the phase shifted PWM for the multi-level inverter. Device switching frequency is same for the all switches. So, you can take the same kind of device. Otherwise, if some switches have a more switching frequency and some switches have a less switching frequency, as we have seen in case of the different level of the cascade voltage 3V and V, it is switching very frequently, the lower voltage, and another it is switching quite less. So, for this reason, but that is a very good combination, you know, IGBT and the GTO combination makes it happens. So, that is one of the better optimizations. So, we can play around. The switch devices usage and the average power handled by the each module are evenly distributed, and thus losses also evenly distributed, and the design of the heat sinks becomes simpler. Better total harmonic distortion or THD is obtained at the output using m minus 1 times lower frequency carrier than the inverter switching frequency. The magnitude of voltage steps change during switching is only E. This leads to low DVDT and reduces the electromagnetic interference. So, these are the major advantage. Thank you for your attention. I shall continue our discussions on the multi-level inverter in our next class also. So, thereafter we shall discuss about different kind of technique, thereafter level shifted technique also will be discussed. Thank you.